Hi, my name is Brandon. Welcome to my channel. Today we are covering protocol-independent multicast. Multicast is a truly extraordinary technology that we use today. If you wanted to stream video or some other service to thousands of computers, you're going to be using multicast to do it. Multicast has many different implementations. There's PIM Sparse Mode, PIM Dense Mode, Sparse Dense Mode, bidirectional PIM. There's a lot of different implementations, but today we're going to discuss and actually configure PIM Sparse Mode. The topology we have in front of us are 6 routers. I've already configured OSPF on all of the routers. They're all within one area, area 0. I've done a show IP route here, and you can see R1 is able to see all of the other interfaces and networks, all the other routers interfaces. The loopbacks for each router, R1's loopback is 1.1.1.1, R2 is 2.2.2.2, and so on and so on. So sparse mode, how do we get it working? First, you need a rendezvous point within your network. A rendezvous point is the interface. It's one of the router's interfaces in the network. It's where you send multicast traffic to if you wanted to reach other devices, as well as where you would request multicast traffic from. Let's say PC1 was trying to send multicast traffic over some multicast group. It would send an IGMP packet to its nearest router, its gateway, R6, and that would be translated into a PIM register. It would then register that multicast group with the rendezvous point, which would now be available to be pulled or requested by any of the other routers in the environment. Now, one of the big questions here is, how do you know where the rendezvous point is? So if R6 wanted to know who the rendezvous point is, it would listen for the RP mapping agent. So this is another router. It can also be the same router. The RP mapping agent is actually going to elect and then announce the RP candidacy and the successful election of an RP candidate. So R4 would elect itself as a candidate, and the RP mapping agent, which again can run on the same router, but in this instance I will be putting it on router 2. The R2, the RP mapping agent, will listen for R4's RP candidacy and then elect it and then announce and flood that to every other router in the environment. And that is how every router would know who the RP is. So let's go ahead and just get PIM enabled, get the process running on all of our routers. I am using the distributed command here that is required for the CSR 1000. If you're using like a Nexus, you'd probably just be doing IP multicast routing. This distributed, what does it actually do? When you say distributed here, it takes all the multicast processing, takes it off of the route processor of the router, and puts it on the actual line card itself. If you were to have a huge burst of multicast traffic and that has to get processed by the route processor, you can have some weird things happen, and you can have some routers hang and just eventually fail. They will stop responding. So we're going to use this and put this to get the process running on every router. Let's make sure that I actually entered that. Okay, now we have multicast routing enabled on each of our routers. Now the next thing we're going to do is something called an AutoRP listener. We're going to also put this on every single router. What this is going to do is it's actually going to listen for specific multicast groups associated with auto rendezvous points, and that's I believe the addresses are 224.0.1.39 and .40. Now, what's going to happen is when a router receives any multicast traffic with that group, it's going to flood it out of all of its interfaces. It's going to treat that traffic in dense mode. The purpose of that is so every router receives that RP information because it is so important. Again, you need to know who the RP is, as well as candidacy and all that information. So we are going to do, we're going to put that on all of our routers here. Listener. Okay, perfect. So now let's actually get all of our interfaces and put them in sparse mode so they start behaving in sparse mode. We're going to use the interface range command, and that'll make this easier for me. We have a variety of interfaces. I'm just going to do interface 1 through 4. That should cover all of our routers. I'm also going to do loopback 1 because I want to include our loopbacks in sparse mode. And, nope, I typed it wrong. If I can type correctly. Okay, I'm just going to copy this. Oh, whoops. We're going to put these in sparse mode. Perfect. I'm going to do the same on every router. We should see DR candidates start to get elected here. Okay, perfect. All of our interfaces are now in sparse mode, and we see these adjacencies. So initially you have these neighbors coming up. These are PIM hellos that are going between these links. On each of these segments, there's a PIM hello being sent by each router, and within that PIM hello, a DR is decided, a designated router. The only purpose of a designated router is, I'm going to use PC1 because it's a good example. If PC1 sent an IGMP packet which was converted into a PIM join to R6, if R6 was not the DR for the link between R6 and R5, if it wasn't the DR, it would actually forward that PIM join to R5, and then R5, as the designated router, has the responsibility of sending the PIM join directly to the rendezvous point. So that's very important. DR is selected for every segment. The connection between R1, R2, and R3, there's actually a switch in between. So this is all one segment. So what's going to happen here is one of these interfaces will be selected as the DR. Now initially cost determines that. So cost is in a metric from the rendezvous point. R2 and R3 are going to be have the same cost towards R4 because they're both directly connected to it. They have point-to-point connections. So it's actually going to defer to the highest IP address, which is going to be R3's 100.0.0.3. So that will be the DR for it. Just giving an example. So now we have sparse mode enabled on all our interfaces. Let's have R4 send out its RP candidacy. Let's have it advertise itself as an RP candidate, specifically an interface. So let's do IP PIM send RP announce, because it's going to be announcing itself. Now it needs to announce an interface. I am announcing loopback 1, and we have to specify scope here. Scope is just a time to live factor. Time to live gets decremented by 1 every time you traverse a router. We only have 6 routers, so I'm just going to make this 6, so that way everything can get from across the entire topology. So now R4 is advertising itself as an RP candidate. However, what we don't have is an RP mapping agent. That RP mapping agent has to see its candidacy, its announcement, and elect it as an RP, and then flood that everywhere to all the switches, to all the routers. And that is how each router would know who the RP is. Right now, R6 would have no idea who the RP is, and therefore it would never, any multicast traffic would not go anywhere in sparse mode. So let's now set R2 as the mapping agent. The way we do that is very similar. IPS send RP discover. So now we are discovering rendezvous points. We're going to specify an interface here as well, loopback 1. We're going to do the scope of 6 as well. That's for time to live. So now what we should see is we should see some tunnels start to form from every router to the RP itself. And the purpose of these tunnels is actually send those multicast streams. Multicast streams only go over tunnels from these edge routers, if you will, to the RP itself. And now we see routers forming. We should see every single router have tunnel interfaces come up. Yep, R1, R2, R3, 4, 5, and 6. Perfect. So we now have successful creation. So if I were to look and see, hey, who is my AutoRP, I should see For R1, it's gigabit Ethernet 1, which of course this is where it's outgoing to get to R4, but can I see RP itself? No, I'm not joined to any other groups besides the RP groups, which is .39 and .40. I can see my neighbors though, which is perfect. I can see my tunnel, and that should be perfect. This specifically, this is our PIM encapsulation. This is specifying RP is 4.4.4.4, which again is that loopback which we were advertising on R4. Now, so let's simulate some multicast traffic, and that way we can have our proof of concept here, and we know this is all working. The way we're going to do that is we are going to have R6. We're going to put one of its interfaces, and we are just going to create a PIM join independently without having any host send anything to this interface. Let's go to interface. This is interface 2, which is actually interface 3, gig 3 here. Let's do an IP IGMP join group, and I will create an arbitrary group here. I'm just going to select this. So now I am part, this interface is now part of this group. So I should have show IP IGMP membership. Perfect. I am now a member of this group. I should also be able to see the RP candidate for the RP for this group. Show IP PIM RP, and yes, for this group, this is my RP, which is perfect. That means this is working. Traffic, anyone who requests this group will go to the RP, and it will successfully be able to send traffic to R6's interface, which is part of that multicast group. So let's have someone, we'll have R1 simulate traffic going to that group. I'm just going to use a ping 232.0.0.1. If I ping from R1 to this multicast group, I should get a reply from the interface on R6. And if that works, that means multicast sparse mode is working correctly. We have appropriately assigned an RP mapping agent, which elected that RP and then floated it everywhere. And now we have basic multicast connectivity. Now let's see if this works. Perfect. Looks like we are getting replies. It's a little delayed. Awesome. Yeah. And I can see 172.16.0.1, which is the interface on R6. Our delay is a bit high there as well. And there it is. So we have multicast working. We've set up our rendezvous point, our rendezvous point mapping agent. We've got all our interfaces in sparse mode. This is a successful sparse mode configuration. Thank you for watching. Please like, subscribe, give me any feedback that you think in the comments. I appreciate your time. Thank you.